Okay, this was a very bad time to start because I'm eating cookies. But no, it's okay. So we're very happy today to have Bigeng to give us the talk, the HIT seminar. So Bigeng did his PhD at Columbia University. Now he's a postdoc at Kentucky University, but we're very happy that he's here physically with us in Berkeley. And he has worked on a lot of different types of lattice QCD calculations related to K-meson, K-meson physics, and more recently also the hadronic tensor. And today he will talk about trace anomaly form factors from lattice QCD. So I'll start whenever you're ready.
Thank you. Thank you very much for the opportunity today to talk about the trace anomaly form factors from lattice QCD. You can find a reference at archive. Before I start, I would like to give special thanks to my collaborators, especially Fang Chen He, and my advisor, Keifei and Terrace. And today, my talk, I will start with an introduction, especially for some of you who are not very familiar with trace anomaly and the motivation that we start the calculation with the form factors. And then I will talk about the calculation of the QCD trace anomaly that we actually did on the lattice from lattice QCD, including the numerical setup and our methods to extract the form factors. Finally, I will present the results with the form factors, mass radii, and spatial distributions that we obtained from the calculation. And follow that, I will give a conclusion and outlook for the future calculation. So first of all, what is trace anomaly? I would like to start with the symmetry of the Lagrangian density of the standard model. First of all, there are a lot of symmetries, which means invariances under transformations. Classically, according to Noether's theorem, a symmetry means a conserved current whose divergence is zero, and which means a kind of a conserved charge associated with that. However, with the quantum effects, there's something called non-symmetries, which are just classically look like symmetries, but actually not. That's why we call it anomaly. Something interesting in our case of trace anomaly is there is a scale invariance from the Lagrangian, if you look at it, in the limit where quarks are massless. So if we do some scale transformation for the field and also the gauge field, what we can find that the Lagrangian density changed some by, for example, here by a scale factor. But if we redefine or change the variable, then the action is not changed after such transformation. So in principle, there should be such a conserved current associated with that. But this is not true with the quantum effects. Here I'm looking at the QCD. And the divergence of this current, Noether current, associated with scale transformation is not zero. And that's the anomaly we're talking about here. So why do we call this trace anomaly? Because if we actually look at this expression of the Noether current, the current itself is related to, it's just a product of the coordinate x times the T mu nu, which is the energy momentum tensor, which included a lot of useful mechanical properties. And if we look at the equation, the divergence of this current, and also apply the conservation of momentum, energy momentum here, we find that the divergence of this current actually equals the trace of the energy momentum tensor. And the fact that this trace is not zero, even when the quark mass is zero, and classically there should be scale invariance, this is not zero. That's what we call anomaly. So now we here have the two word trace anomaly ready. But what is the physics related to the trace anomaly induced by the QCD effect? So the physics is a hadron mass. So if we look at the matrix element of the energy momentum tensor, and we take the trace of that, we'll realize the matrix element in the forward limit should equal the mass of the hadron. If this matrix element is actually 0, then which means all hadrons are massless. However, we all know, in fact, in nature, the trace is not 0. There are 2 contributions so that all hadrons are not massless. First of all is what we call the sigma term, and that comes from the fact that quarks are not actually massless. So, and the second one is the term that we mentioned. Even in the limit where the quarks are massless, we still have a trace anomaly induced by the QCD effect. So in total, here I should mention the notation here. The bracket I have here with the H label here actually means kind of a matrix element divided by its normalization. So this whole thing is independent of the normalization of the state. But for now, we look at the expression. There are 2 contributions. One is the sigma term, one is the trace anomaly. So
the fact that I have a lambda QCD which is not 0 already, isn't that already showing up related to the trace anomaly? So if I start with a dimensionless theory, if
yes.
I have no quark masses, and then the dimensions get dynamically generated, right?
Yes.
So, okay.
Yes. So yeah, that's why we have actually absolute scale actually
Right.
here. Yes. So one may wonder or naively think about, oh, maybe this trace anomaly is not so important, and naively think about maybe the hadron mass comes from the fact that all quarks are not massless, and if all the contributions from this fact. However, if we actually evaluate the sigma term, we realize and compare that with the actual hadron mass, we find that sigma term is very small. For example, it's very small in the nucleon. There are calculations which calculate the sigma term, which is only about 8.5% of the nucleon mass. So actually, the trace anomaly term dominates in the mass of the hadron. And also for the pion, if we use the Gell-Mann-Oaks-Wiener relation and the Feynman-Hellman theorem, we can show that the sigma term contributes about half the pion mass. So as a result, the trace anomaly term should contribute another half. So in order to give all the contributions to the hadron mass, we need to include the trace anomaly term also.
The pion, yeah, that doesn't make sense for the pion.
Exactly.
Because in the pion, you send the quark mass to 0, you get nothing.
Yes. Yes.
So then the trace anomaly.
Yeah.
That term doesn't vanish in the mass.
Well, he has a mass term in his trace.
Not F squared. Well, you will mention the mystery. There's a mystery there. He will
Yes.
talk about the puzzle. The
Yes.
puzzle mystery. Why it goes up with the square root.
So actually, that's something I'm going to mention later. But if we only look at sigma term based on the Gell-Mann-Oaks-Wiener relation and Feynman-Hellman theorem, sigma term contribute about half. And if the sum rule holds here, then the trace anomaly term should also approach 0.
So what is this gamma m up there in your?
Yes. This expression actually comes from if you do a dimensional regularization of the trace anomaly, and you try to deal with operator mixing, then this gamma m is the the anomalous dimension, and the beta over 2g is just what you usually have in the RG equation.
So why is that gamma m term not in the sigma term?
Oh yes, the way we separate this two is based on this whole thing is generated belongs to the trace anomaly.
That's how you define it. For what reason? Why don't you lump it over to the sigma term, this gamma m term there?
Yeah, I guess there are several reasons. First, sigma term by itself is RG invariant.
Okay.
And also, if we do not do any renormalization, there's only a F squared operator here. This term only happens when I try to renormalize or do dimensional regularization, and this term comes out. So that's, but it's actually a result of this F squared.
Okay.
So that's why I combine this together. And also this term by itself is also RG invariant. So that's why we usually write this way. So as a result, trace anomaly is very important. And if we look at the origin of the nuclear mass, that's a kind of major scientific goal of the EIC at Brookhaven. And there are a lot of theoretical and experimental efforts try to understand this subject. And also because the trace anomaly term by itself is highly non-perturbative, so it has better be evaluated with lattice QCD, and this is a work by some of the authors of the current work as well.
Good.
Yeah.
This trace anomaly, is this just the leading order for QCD expression, or is this like in all orders?
You mean this expression here?
Yeah.
Yes, I think it's written in a form that it contains all the orders. Just a kind of a form that I've written down. So after all the renormalization, you have a beta over 2G renormalized and F squared renormalized and gamma M, all these things. So, but for now, I'm just writing everything in the form that from the dimensional regularization and from a kind of perturbative expression.
So in the chiral limit, the pion mass should be then only given by this F squared term, right? Or is this gamma M times M term still there in the chiral limit?
In the chiral limit, that's what we.
Oh, it's coming? Okay, then.
Yeah,
then,
yes,
then,
right.
okay, then I made.
Yeah, thank you. So what really motivates our calculation is what called the pion mass puzzle. Because if you look at this equation of the pion mass, if you look at the SU2 chiral perturbation theory, especially the gamma-Oaks-Rayner relation, which I have shown here, the left-hand side, which is a predicted pion mass, can be found here, which is proportional to the square root of the light quark mass. However, if we look at the right-hand side, the sigma term, we can also predict its behavior from the Feynman-Hellman theorem. And using this, combine this with a gamma-Oaks-Rayner relation, we can find that the sigma term is about just half of the pion mass, which is also proportional to the quark mass. So if this equation holds mathematically, the trace anomaly term must also be proportional to the square root of the quark mass. So the puzzle is that as we are approaching the chiral limit, the sigma term disappears, and also the trace anomaly term will also disappear in a manner which is proportional to the square root of the quark mass. So the puzzle here is, as Kefe proposed originally in this paper, why does the trace anomaly, which is actually come from, which is a conformal symmetry breaking term, have a chiral symmetry related behavior, which is proportional to the square root of the quark mass in the chiral limit. And another question associated with this question is, what kind of structure change can facilitate this attribute for the trace anomaly when we're approaching the chiral limit? So the natural thing to think about is if we can look at the spatial distribution of the trace anomaly and how that looks like as the quark mass gets to smaller and smaller.
So I guess, yeah, there's some integrals missing here, right?
Yes.
There's some hidden integral, yeah, so, okay, because the operator itself, the F squared density will go to 0 just because MQ goes to 0. So you're saying it's the integral of F over the hadronic wave function of pion, which has to go root MQ or something.
Yes. So then the key problem we are going to tackle is what is the spatial distribution of the trace anomaly and how that changes in the chiral limit. So that's the kind of figure showing we're starting with some problem with the hadron mass, and now we're trying to look at what are the distribution of mass from the trace anomaly term. So there is a previous calculation by our collaborator try to answer this question, and also our author of the current paper. They look at the contribution from the F squared term, the glue term, from in the trace anomaly. What they actually look at is a 3-point correlation function on the lattice, which is the Euclidean space correlation function. And the distance R which appears in like the position of the operator, is defined as the distance between the current insertion and the hadron at the sink. So they actually define a density, which is the contribution to this total trace anomaly within this shell volume, and divide that by the volume. They define such a density. So if we plotted such a result of such a density for various quark mass. So when the quark mass are very heavy, for example, like here is the pion mass correspondingly is about 1.6 GeV, which is very heavy. The density is mostly positive. As the quark mass gets smaller and smaller, we can see the integral of this curve. This curve gets smaller and smaller. But something interesting happening is when we get a relatively light quark mass, the density defined here start to change sign. So the negative and positive part start to cancel, and so that the total contribution goes to 0 in a square root manner. So that's here we see here the defined that this rho density function changes sign in this study. But one may ask question is why not we just calculate the trace anomaly form factors?
So hold on.
Yeah.
F squared can be negative in your Euclidean world, is that?
Yeah, because here the matrix element we have already subtract the vacuum expectation.
Okay.
So the negative
Relative to vacuum. Vacuum's negative.
Yeah.
Okay.
So yeah, so it's relative to vacuum is negative. So, but such a definition of density is not that very straightforward. So the direct way is we can think of why not calculate trace anomaly form factors. So from matrix elements, form factors to spatial distributions, why do we calculate this? The analogy or something similar is the radius distribution. All these kind of things can be obtained for the electric form factor, and from which we can calculate charge radius. So for example, for the neutron, we can have experimentally measure all these form factors, and by performing the Fourier transform in the bright ring, for example, then one can get the spatial distribution of charge within neutron, which is negative here and positive there outside. So that's something people did in the electric form factor.
Isn't that the other way around? Positive inside and negative outside?
I think here, yeah, from this one it's negative.
They just probably inverted the sign.
Yeah.
Oh, this is
This is a neutron charge inside. I think
it should be. It's the old-fashioned way is made of neutron is pi minus and p proton. Pi minus outside. So therefore, if you look at the skirmion and so on, then it will be negative outside and positive inside.
Okay. Maybe I should check the definition that they're using.
Yeah, I'm not sure what that's the usual way of understanding neutrons.
Okay.
Negative outside.
Yes. So here we're doing something similar. We're trying to calculate the form factors. So for the trace anomaly. So also another thing related to the form factors is all these things can be measured. For example, the charge form factor, electric form factor, you can measure that experimentally and turn that into a spatial distribution. So why not calculate trace anomaly form factor? That's our idea, so that we can get a spatial distribution as well. So first of all, we need to find out the relationship between the matrix element and form factors. First of all, the trace of energy momentum tensor is a scalar, Lorentz scalar. So we define accordingly a dimensionless scalar form factor and have such a relationship between the matrix element we have and also the form factor we would like to calculate. And one thing we can keep in mind is under such definition, the form factor here, the scalar form factor here, in the forward limit equals to 1, so that we get a total contribution of mass of hadron, which is in percentage. Here it's just 100%. And the other thing after defining the form factors, we need to figure out the relationship between the form factor and the spatial distribution. So we can follow something very similar to the electric form factor, where we can define a mass radius from the derivative of this form factor. And also correspondingly, we have a three-dimensional distribution, for example, in the bright frame. And we simply perform a Fourier transform for some of the, for example, here, the nucleon here. However, it has been pointed out that such expression, definition of the spatial distribution, are only valid for non-relativistic systems. So if this condition, where the size of this that you obtain from a form factor derivative is not that larger than the Compton wavelength of the particle we're interested in, then this such definition of the spatial distribution is not quite valid. So, but we are going to look at pion in our case, and including nucleon. So alternatively, we have another option. It's just one of the options where we have a two-dimensional spatial distribution in the infinite momentum frame, which here in the limit that the momentum within the z direction goes to infinity. And this is also an elastic frame. So in this frame, we can perform a two-dimensional Fourier transform on this form factor to obtain a corresponding spatial distribution in this frame. So the details can be found in this paper as a reference. So that's our way to convert our form factor to the spatial distribution. So finally, we reach a complete picture where we have defined form factors from matrix elements, and we are going to calculate the spatial distribution of mass within hadrons. So now I'm going to show the detailed calculation that we perform on the lattice. So first of all, because all the sigma term and trace anomaly by itself is RG invariant, so we can simply decompose this form factor into two parts. One is from the sigma term, and one is from trace anomaly. So, but in our calculation, we're only calculate for now just the glue part of the trace anomaly, based on several reasons. First, in the nucleon, the sigma term by itself is very small, and if we neglect the term which carries the gamma m, then the glue part dominates. And even in the pion, if we assume also the gamma m is not that large, then the glue part also dominates the trace anomaly term, which we're interested in. So for now, just temporarily in this work, we calculate the glue part and call this trace anomaly form factor GH in our calculations. So all we need to do is replace all these form factors in the previous slide with this G factor for the glue. And everything else just follow the same way.
So what is a gluon in your case? Is it a mixture of something, or I mean, isn't that a question of scale and God knows what? So how do you define that?
The bigger question is, how do you define beta and G?
Yeah, right.
Yes, in principle, everything is defined from starting from the specific operator, the F square operator and psi bar psi operator on the lattice. Everything here is kind of using the form of the perturbative expression.
Yeah, but you have to plug in a number for beta.
Yes.
And presumably the choice of that depends on Volker's question. What do you mean by a gluon?
Yes. Our definition actually starts. It's a little bit tricky. Is we start from these operators F square and psi bar psi, and if there are some still other mixings with lower dimensional operator on the lattice, but we can get this beta over 2G and gamma m from the sum rule to help us.
How do you get the rules of it? Are you going to talk about it in more detail? Or?
Yes, I will. If time allows, later I will talk in detail how we calculate this beta over 2G and gamma m using a non-perturbative way on the lattice using the mass sum rule. But for now, we just keep the similar form And on the lattice, we use operator f squared and psi bar psi in our calculation. Here we just calculate the f squared on the lattice. Also, we're looking at the fact that this whole thing is RG invariant. But yeah, I think that's some details later when we talk about how to normalize these things on the lattice. But for now, we do not have actually some glue in mind. We just apply this operator f squared in our calculation. Okay, so then the problem here now becomes how can we evaluate this matrix element? So that's why we do it non-perturbatively on the lattice. So in contrast to the perturbative way where we define the observables in the Minkowski space, where we can evaluate all these correlation functions, where we also do perturbative expansions. Here we perform a weak rotation on the path integral, so that everything is now converted to the Euclidean space. And this may look familiar to some of us, that this is a partition function if you look at it in a statistical mechanical way. So the observable here now in the Euclidean space looks like an ensemble average for an ensemble with distribution defined by this action. So the next step is on the lattice, because in order to generate such a distribution, but here everything is, the degree of freedom is infinite. So all we need to do is to make it manageable to be calculated is the discretization of space and time. That's why we have a lattice. And on the other hand, we need to generate kind of using Monte Carlo method, such action, which reflect the physics of QCD. After we've done this, in order to do this, we need some input parameters, for example, lattice spacing, quark mass, and also the coupling that we have for a specific ensemble. But everything here is non-perturbative. Once we get these ensembles, we can calculate some endpoint correlation functions, and based on the Wick's theorem, all these correlation functions can be evaluated by the contraction of propagators that we obtain on the lattice, and from which we can extract hadron spectrum and matrix elements. So specific to our calculation, what kind of observables do we measure on the lattice? So here we are looking at the trace anomaly form factor. So first thing we can think about is the 3-point correlation function, which is constructed from interpolating operators here. So there are 3 points, including 2 interpolating operators, which has the same quantum number as the pion, for example, that we are interested in at time 0 and the sink at time t. And in between, we insert a current. Here I'm using the current f squared inserted here at t equals tau. So what does this expression mean? We can look more clearly when we insert some intermediate state between these operators. And in the limit where the source sink separation, time separation is very large, and the current is very far from the source or sink, all this 3-point correlation function reduced to a relatively simple exponential, and we see that the form factor we are interested in appears here. But we also notice, in addition to the form factors we're going to calculate, there are still other extra parameters like the energy of the source state, source ground state, and the sink ground state, and also the overlap factor between the interpolating operator and the pion we're looking at. All these extra parameters can be constrained if we are calculating the 2-point correlation functions as well, because if we look at the 2-point correlation functions, the same parameters appears as well. So in order to extract these form factors, we perform a 3-point and 2-point function joint fit. So finally, we can extract this form factors from the fitting. In order to get a relative comprehensive curve of the form factors, we take several momentum and source sink momentum combinations. First, we set the source at rest and let the sink has momentum. So these are only relatively small momentum transfers, so like the red dots here, in a very relatively smaller region. In order to reach a larger region, we have a back-to-back case where the source and sink have opposite momentum, so they can reach relatively high energy transfer within the statistic limit that we can have. And in between, we use some near back-to-back case, so they're not exactly back-to-back, but they can give more data points in between. And here we also use a grid source to increase the statistics. So that's why I draw different colors to denote them here. But the key point is with this 3-point functions with different momentum transfer, we can obtain the fitted form factor from that. And because we are going to explore the quark mass dependence of the form factor and everything else, so that we repeat this process for 7 valence pion masses. So that's our kind of summarize all the results we have for all these different masses. So finally, something tricky here, just specific numerical here is, in order to preserve the chiral symmetry, so we use the domain war fermion configuration and with such input parameters. And also other parameters like how many configuration we use. And on the other hand, to obtain these propagators on the lattice, we also need to have a lattice action or fermion action, which also preserves the chiral symmetry. So here we're using the overlap fermion, which for overall we have a good chiral symmetry in this calculation. And finally, with several quark masses, by the way, that's the renormalization issue I'm going to talk about later if we have time. After renormalization, we can obtain something physical by doing the chiral extrapolation so that we can have some form factor radius and then spatial distribution at the physical quark mass. Okay, so now I go through all the formalism where we have to extract these results. So I'm going to show the results we have. So first, I would like to show something related to hadron mass, especially something we're interested in for the trace anomaly in the forward limit, which especially for the operator f squared that we have. So first, here's one of the quark mass. All we need to look at here is just a zero momentum transfer, which is just a dot here. First of all, it's positive because it's actually the contribution to the pion mass from glue. And if we look at the kind of a prediction from chiral perturbation theory, that prediction is also a positive, which is 1/2 of the pion mass. By assuming the gamma m is negligible, then that's just 1/2.
I thought it should be 1 your form factor, the way you said this before.
Oh yes.
The forward limit, right? Why is it not? Is it 1 maybe?
Yes, it's the trace anomaly part. It's 1/2. So
that's
including the sigma term, then it's 1. For trace anomaly only, it's just 1/2. Okay. Then we can look at everything with 7 different valence quark mass and see how that looks like. So previous, I've shown that the pion mass is proportional to the square root of quark mass and also the sigma term, and the trace anomaly whole thing is proportional to the square root of quark mass. But something interesting is what we find here is not only the trace anomaly term is proportional, it seems that the f squared term that we are calculating here by itself is also looks like a proportional to the square root of the quark mass. This is something I think very interesting is feel like the F squared term also know something about the part mass as well. So that's for in the forward limit. And also I will show the form factors that we get. So in the forward limit, the form factor is positive, while at larger momentum transfer, the Q square is just negative. So there is a sign change here in between in this region. So this sign change is also predicted by the chiral perturbation series. So if we look at the trace anomaly term here, then there is a sign change at n pi squared. So this is kind of consistent in some way. But something more interesting I would like to show is not just the sign change of form factor, but we actually look at the spatial distributions that we get. So in order to do that, we need to perform the Fourier transform, and therefore we need to fit this form factors, the discrete points with a functional form. And here we use the Z expansion fit. So we fit everything in the data region, and we can kind of extrapolate to a relatively large momentum transfer. So that's the kind of fitted form factors we have. And after
it's kind of hard to read the legends from here.
Yes.
Pion masses.
Oh yes, it's 0.25 all the way to
0.25
or
GeV.
yeah, GeV, and the largest one 0.539 GeV, which is about 540 MeV.
How do we understand it? Like, can you describe the trend so I don't have to think about it?
You mean the trend here?
Yeah. Like what do we learn from the spots?
Oh, this is just not just some trend I would like to show. Just to show we perform the expansion fit from this data point. So we have a kind of continuous functional form to perform Fourier transform.
Okay.
So something interesting here is after we perform the Fourier transform from the form factor to spatial distribution, for the pion, we actually find out that previous in that paper, there is a sign change in the rho h that they defined. Here we also see a sign change for the spatial distribution. And here the mass are from low to high. And we can see the kind of the sign change location gets larger and larger as the pion mass gets lighter and lighter. So that's kind of something we can not easily to see from the back, but it's just as the mass gets lighter, the node kind of gets further away from the center. But there is a sign change that kind of we have seen
Would be
here.
interesting to sort of plot this at 1 over the pion in units of inverse pion mass or inverse quark masses, right? Because if you make your quark mass lighter, then the wave function which integrates over this distribution gets larger, and therefore I could see that this thing averages to 0. But I mean, for that one needs to see the scale. So what is the Pauli wavelength of your quarks? Does that actually cover when you have a small quark mass? Does that actually cover both the negative and the positive? It would be interesting to plot this like that.
Wait, what is the you want?
So how can it come that this the integral over this thing is 0 when it goes to the chiral limit? That's what we found before, right? That the contribution of the trace anomaly goes to 0, as it should. Otherwise, you wouldn't get a 0 pion mass. And the only way I can understand this, if you have now these quarks and you have this gluon condensate, and now the quarks run around and they sample this whole gluon condensate. If the quark wave function is wide enough in R, then you integrate over the negatives and the positive, and it could very well just average to 0. Right? Whereas, well, I mean, you have your, as I think about this, you have your gluon condensate sitting there, and then you have your quark propagators running through this thing, right? And if these quarks are very heavy, then the average distance between the two quarks is of the order of the quark mass, right? So they never probe the whole thing. But if the quark mass is light, then they
You
broke.
can go to.
I mean, I'm just making this up as I go, right? But
The quark does not contribute to this property, right? It's F squared.
but the wave function of the pion does. I mean, you broke this thing with the wave function of the pion.
What do you mean by wave? The quark wave function or glue wave function?
I'm very
You
confused by
have a Fox space of many things, right?
Yes.
And this is the Fox space for the glue so far, without mixing. the
Wait, what do you
quark.
mean by that, Cafe? I don't understand any of the things
Oh,
you're
I'm
saying.
thinking that if you have a Hamiltonian approach, right? This is you have a Hamiltonian, you look for F squared and side by side and trying to calculate that. You have an E0, and then you have presumably the pion will have QQ bar, presumably pion will that's
But
probably
you're-
the
but you're
the dominating part is the QQ bar part of the Fox space. And glue for some reason, I don't know nobody knows what the wave function looks like. We only have the spatial distribution. Turn out it contributes more, and okay, I don't know. Let's say I don't know. If I look at the pion, normally we think, the other things, the rho and the nucleon, the quark dominates, right? Then you have a 3 quark or 2 quark and a quark, that's the major Fox space. The others are pion or pi are modifications. Now with the glue here, I'm sorry, I am lost. I don't know
I mean,
how to
definitely the
think
quarks
of the Fox.
contribute, definitely, I mean, you said something like the quarks don't contribute here, but definitely they do, right?
The quark will contribute to the
The
side by
sample
side,
size,
side
right?
peak, yeah.
No, but it also, I mean, the fact that it drops like the square root of the quark mass. That's what you showed in the previous.
Right.
Right, that's what I'm trying to understand, how
True, yeah.
this comes from. right?
He would make a conclusion.
Okay, all right,
We
that's correct.
we know how but not why. But that's something.
Can I ask a more simple question? You're making a lot of emphasis on the sign change, and I missed the importance of the sign change. I mean, is it just because it has to, maybe explain it again, sorry, I missed.
Yeah, I think this sign change is something we didn't expect, but actually we see here. I think from the form factors there is sign change, and
You should probably go back to the neutron except were you here in the neutron? Well, you should probably
But
go
how
back.
can it,
Yeah,
how can
neutron
it come
is
to
more-
zero if this condensate is everywhere positive or negative?
So it's,
So-
okay,
Right,
so
I
it
mean,
either integrates, either the integral is zero because there's a sign change.
Or everything is zero, right?
Everything's zero.
yes,
yeah.
But
that's right.
the trend is different, like the quark mass, the amplitudes get larger, right?
That's the one that wrote in the paper. The puzzle was that if you consider nucleon, all the energy comes from the trace anomaly, 90-some%.
Yeah.
You can think of it as coming from the condensate. Many people mention that. You make a hole. The condensate itself is negative.
Yeah.
You make some volume, right? And then somehow it's
Functional.
positive. Now,
But
that
that's-
defines the volume. But
Right.
here in the neutron pion, what does it mean? The volume goes to zero? As it's a one way, is a uniformly goes to zero. And the other one is this, they just shifted to get the vacuum even more negative and put the stuff outside to be positive. That's something which is envisioned because of the example of the neutron charge radius, charge form factor, but you have to show it in a realistic calculation. That was the story so far. I mean, I should have let you answer. You are the one who's supposed to do that.
Yeah. I think originally, from this calculation, we see how this whole thing goes to zero as the quark mass gets smaller and smaller. It's not just by just the whole thing shrink all the way down to zero. It's actually achieved by the negative at the light quark mass, the negative part and positive part kind of cancel each other, so that the total distribution goes to zero in the chiral limit. But also that's what we have found here in our calculation. But something we have in mind is what Kefe just said. If we look at the neutron charge distribution, there is some negative part here and the positive or change the sign opposite way, but they kind of cancel each other, and overall the charge distribution, overall charge is zero. So we have something similar here, but I think it's probably in Kei's paper talking about the confinement mechanism of the hadron, where he the role of trace anomaly and the quark, where he's thinking about see something here is the sign change is that inside it's just like a hole in the vacuum, and something out, and over in total this contribution goes to cancel each other, and in total it goes to 0 in the chiral limit.
So I think maybe to Volker's point, if the x-axis on the middle plot was in units of the pion mass rather than Fermi,
That's what I want.
That would suggest how much of this is inside the.
Yes.
The inverse pion mass is roughly the size of the.
Yeah.
Or the quark mass maybe.
Oh, I was thinking the pion mass, because that's what sets the hadronic.
I mean, a chi by I gives you, they should fall on top of each other, at least the transition should fall on top of each other, right? I mean, the yellow curve is 500 something, and the blue curve is about half, right? So just by eyeballing, right? I mean, that would be interesting to make this plot.
We go back to look at
Or maybe you have it already.
Novikov and Schiffman. Novikov and Schiffman, they looked at J psi prime to J psi to the blue. And that's what happened, minus 1 over n pi squared. So the R square is proportional to 1 over n pi squared.
Oh, you mean the
Look
node
at that
point?
expression. Yeah. So as you said, the smaller the smaller quark mass radius to
Exactly.
as 1 over the F squared goes to 1 over n pi squared.
Right.
Yeah, precisely.
So it would be interesting to see the density units of 1 over m pi and just look at the curves.
Yeah. That's a very nice suggestion. I think later I will just plot it, show that, and should be clear the relationship.
And pi will be right.
Yes.
In the rightmost.
Yes.
So why is this GV cube, but the plot from the other paper was in GV to the 4th?
Yes, I think it's actually related to the normalization of that rho defined.
Okay.
So I think there is a normalization difference here.
Is it a factor of the pion mass difference, or?
It's one thing here is we have a 2 pi r times rho, rather than here we have.
Oh no, I don't mean, so that one I understand,
Oh,
but
yeah.
I mean, so the one on the right, this plot of
Yes.
rho h
Yes.
is in GV cubed, but the analogous plot from the older paper that you showed in the beginning was GV to the power of 4.
I think here there's someone is normalized differently.
You have to squeeze it.
Okay. This one is a kind of normalized one, while the previous one there's no normalization with respect to the center value. I think the value at the origin or something.
Okay, so it has like an extra factor of
Yes.
rho 0 or.
Yes.
Okay.
Yeah. So here is a bar here. In that plot,
Oh.
there's no bar.
I
So,
see.
yeah.
Thanks.
So this one integral equal to 1.
This integral should equal to the after the integration should be the contribution from the glue to the total mass.
Forward integral.
Yes. This is just a spatial distribution. And we sum them up. There should be the f squared in the 4 limit. Okay, so we have something quite consistent with the previous calculation with that density. On the other hand, we try to calculate the radius of the glue trace anomaly, and by doing this derivative with respect to the q squared, and we extrapolate the result. We have seven quark masses, but we do not have the physical quark mass. So we try to extrapolate this using the functional form predicted by the chiral perturbation theory.
It's a lot of cases in chiral.
Yeah, and also
No, it's a one-off.
Large systematic errors.
One-off.
and also we by adding without adding this term, we see a large difference in the results of extrapolation. So we have a possibly very large systematic error here.
Is this all defined including the beta over G, or is this without the beta over G?
Including the beta over 2G that we calculate, which is actually scheme dependent.
Yeah, that's the biggest problem I have is it seems.
Yes.
I can understand putting an F squared matrix in a hadron, because that's F squared on its own is RG invariant.
Yes, it's F squared.
Well, you have to put the gamma m in it.
No, F squared is RG invariant. That
That's
just
F
shows up.
squared?
Yeah, because that just shows up in the action, right? But once you
But without beta over to G.
right,
Yeah,
and so now you're
so-
multiplying by some RG.
Right, but beta in general have a mu dependence,
Exactly.
and then cancelled by the gamma m, so it's together.
No, right, that's why, this is the biggest problem I have with understanding this. is how
You have to
define-
incorporate
how
finite
you
mass.
define the beta,
Right, this is
because that's a scheme dependent thing.
this is the major issue here, visualization, and we can discuss that after that.
But your
Yeah.
G has somehow included the beta over 2G in
Yes.
the definition of the form factor G.
Yes, we include that in our calculation. Yeah.
So why not just compute the F score?
Because finally we would like to see the trace anomaly form factors. So which requires beta over 2GF and also the gamma m.
But if you compute the F score, it's fun too.
Yeah, beta over 2G,
It's a factor.
beta over 2G is independent of the hadron.
Yes.
That's precisely the point, that
So-
yes.
You should be able to observe that the matrix element of F squared itself goes to 0 in the pion, irrespective of multiplying the.
Sure, beta over 2G on the final lattice is just a number.
Yeah, just a constant.
Right, so I guess multiplying by beta over 2G
It's
seems
just
like
a number,
it's
so
it's
On the
math.
finite lattice spacing, it's just a number. The question is, how do you extract that number and gamma m on a particular lattice spacing that you have, which is independent of quark mass, but only dependent on lattice spacing. Maybe we should discuss that point.
So question, so you say current calibration for the RG, somebody calculate that?
Yes, I think you can, naive one,
Make use of formula.
use the soft pion theorem and.
Also,
gravitational-
they just computed that form factor.
Yes, you can use.
I'll use small q squared.
Okay.
That also confuses me, I guess, because beta doesn't show up as a ground position.
Yeah, this is a tree level in some way. But if you actually have like higher level.
They also know that this beta, that the trace element contributes to half of the pion mass, so
Yeah, but what I mean is like,
they coined that term.
the parameter beta and G don't show up in ground perturbation theory, so there's gotta be some.
Eventually, I would say not chiropractic, but Novikov and Schiffman was the first one. What they did is J psi prime to psi and 2 pi. So J psi prime to psi, you have 2 gluons, and they consider that to be, if you normalize that and all that becomes a G mu nu squared. So you have a vacuum, the G mu nu 2 pi pi, and then use the chiropractic, soft chiropractic, move 1 pi onto the other side, becomes whatever the G mu nu square operator inside the pion state, and that's how they, using some other Q5 operator commutator to obtain that relation. Whereas Chen used chiropractic with Chen and the Savage, they have a chiropractic theory which they define the trace anomaly got the same expression. Hata, when he visited here, he used the gravitational form factor yet another way and got the same expressions. So so it's not all, well, they use some chiropractic argument, but not only Chan's paper is purely chiropractic. The others not exactly perturbation, but
It's Junwei.
yeah, it's a some combination of various effects.
Yeah, I think in Hata's way, there's he also applied the soft pion theorem in this case, but yeah. Okay, so but for pion here, we because we do not have any data point at physical quark mass, So such extrapolation may have large systematic error, so which we are going to deal with in the future.
Why don't you explain just jump to the discussion of the debate of the G, that's the major, the crux of the matter, the others are not that important.
Okay.
You don't know the results.
Oh, what about the proton result?
Proton is there.
Oh yeah, maybe I quickly go through the proton and then we can discuss the normalization stuff here. Sorry. So similarly, we look at the proton, the form factors where the trace anomaly term dominates. We didn't see any sign change in contrast to pion. And that's also consistent with the previous results where there's no sign change as well. And also for the proton, we try to calculate the radius of the trace anomaly because the trace anomaly dominates. So the mass radius is almost just coming from the trace anomaly. So we did a similar chiral extrapolation, and we use this term and without this term, log term, to use that as the estimate of the systematic error in the second bracket here. But trace anomaly, our way of calculating trace anomaly is not the only way here of calculating the mass radius. For example, here we calculate a trace that we have these operators like f squared and psi bar psi operator calculated. And on the other hand, the energy momentum tensor, the matrix element can be expressed in terms of all these gravitational form factor A, B, D, and C bar. And one can, from the trace part, extract like A and C bar, and from the traceless part, one can extract A, B, D. And for details, you can check Wang and Dimitra and others' work here. So in principle, we can calculate trace anomaly from these operators that we have defined. Also, we can also calculate the trace, express the trace of the energy momentum tensor in terms of these gravitational form factors. So in some way, it's the same thing. So we can compare them and show that the trace anomaly, if we neglect or include the form factor from the sigma term, then we can calculate the radius of the trace anomaly from all these gravitational form factors. So here I compare our results, which we calculate with the trace, and also several recent calculations. I'm sorry, the font is too small. By Dimitra, using their results of the gravitational form factors, and also holographic calculation, and including Yuxin's work using the lattice data and also fitting of the experimental data. But all these results are quite consistent with our results. While this one, we find a large discrepancy, which we need to figure out later, but there is a discrepancy between this one, which is a direct dipole fit to the glue X data. Okay, so as a conclusion, we have demonstrated that we can calculate the trace anomaly, including maybe I should talk the renormalization later. But we have demonstrated that we can actually calculate the spatial distribution of the mass within hadrons from the trace anomaly form factors. And we calculate the pion spatial distribution, we find a sign change, which kind of is strongly support the hadron confinement mechanism proposed. And also we calculate the nucleon. We find no sign change for the nucleon, and the mass radius is consistent with several other calculations. So the outlook is, for now, we only calculate the spatial distribution of the x beta over 2g times f squared, which is by itself not RG invariant. So in the future, we are going to include also the operator psi bar psi and also the sigma term, so that we can give a comprehensive calculation of the mass distribution for these hadrons, and also for rho mass, we're going to calculate next. And also for now, we don't have a Park mass at the physical point, so that's what we are going to include, and also other lattice spacing so that we can extrapolate to the continuum limit. Yeah, I guess that's the conclusion and outlook, but I think there might be some questions related to normalization, but we can stop here for now.
Can I first ask a stupid question?
Sure.
So what would you get if you did this in quenched?
Quenched? I think we are in some way partially quenched.
I'm puzzled by myself, right? I mean, in quenched, the QM configurations are not affected by the presence of
I suspect you get the same thing. Because the pion mass also goes to,
zero.
yeah, goes to
Yeah,
zero.
but
In a quench
but the
mass,
Q is not affected by the presence.
it will be
The pion
affected.
mass doesn't go to zero.
Sorry?
Well, in quenched, I thought so.
Look, there's a hairpin similarity that causes it to blow up. Yeah,
What is it, bro?
the pion mass in quenched QCD goes to infinity as you take the quark mass to zero.
Oh, yeah, the quenched kind of locks.
Yeah, there's a,
Yeah, there's
Term-
there's a quenched Carol, we wrote a paper on that.
yeah,
Yes, that's a little tricky.
Yeah, but that's what, and then, okay.
If you go into, this is very small quark mass region, you go away from that region.
So you think you would
The pion-
first see the trend before it goes
Right,
crazy?
we see that the Carl lock is very clearly seen, the overlap of fermions with quench. If you go away from that region, maybe.
So, but that, I mean, the reason why I asked is, so can I think about this in terms of the instanton model, this whole thing?
I don't know, I have no idea.
I mean, there I have a simple model which gives me the two fluctuations.
We have never seen instantaneous. When you go to the continuum limit, it's just evaporated. That's another issue, another argument, we'll never be able to.
So
convince-
Ishmael did tons of calculating. It's
He did this for a fact?
Yeah.
Yeah, and it comes out. I mean, but I'm interested in whether you actually get the positive negative. That's-
very good question. So I had some discussion with him. He told me that symptotically the form factor for pion goes like around Q score or something like that. So, but in my calculation, I got a constant. So,
Yeah.
so I told him the power content doesn't work for his model, but he gets almost everything correct.
Yeah.
I mean, he also have this small Q square behavior. So I actually have a question, if I may.
Yes.
So that's related to Dimitri's work. So can you go by the nucleon comparison? Yeah, I mean here, last equation here.
Last equation.
Yeah.
Yes.
So in order to plug into the matrix calculation, you apply the calculation for A and D, right?
Yes,
So in the comparison.
yes.
So it's actually very important point because somehow was not appreciated before. So here it really depends on D0.
Yes.
So D0 is very important. But I was thinking because Yuxin and I were working on GPSI and there it's not easy to access the D easily. I mean, so D form factor only make a significant contribution when it really goes to threshold GPSI or adenotity. Adenotity doesn't help here. So, and for your calculation, it's also difficult because the form factor proportional Q score, right? At Q score goes 0. So in order to get the D0, that's why you have a significant larger uncertainty when you compute the D at equal 0.
Yeah, exactly.
So we
And
will
also
have.
you cannot get it at equals 0. You have to.
Yeah, that's right. You have to take as a limit because when you compute the matrix element, it's proportional to T, right? So it's so that's actually it's very good, very important point. We have to keep that in mind. Maybe the way is just doing what you did, so compute the F score directly. So I don't know.
And also the sigma term, I don't know how, we don't, no idea how large the sigma term. There's a sigma term, you don't wanna just the trace anomaly part.
What about the pion? So I guess in the case of the pion, there's also a relationship between the
Yes.
radii, right? But their your result is very different, right?
I haven't personally checked that one.
Oh, okay.
Yeah, but I think probably from Hackett's paper, I can also calculate. Yeah, but previously I only get the nucleon one to be compared. But I didn't check his result for pion.
Nucleon also have a B term, right? Pion.
B term.
No, B term is sum altogether equal 0, so that's fine.
Yes.
But the R squared may not be 0.
No,
Forward matrix only
no,
0.
no, when you compute the form factor, you compute total form factor.
True, but the quark and glue form factor may not be the same as the Q squared.
No. Here you relate the trace part to your total form factor. That's B just doesn't contribute.
No, the B of Q squared is not 0. B
before-
of Q squared is 0 is 0.
No, I understand.
Yeah.
So here,
The B of Q squared is small but not 0.
I think even for finite Q,
No, it's not.
there's no rigorous proof, but people believe that it's also
A
cancelled.
lot of people believe it. But
There's Stambrowski's Nikon.
it's all forward. It's forward.
No, they also-
all forward 0.
No, they also put a Q score. You can go back.
We did a quench approximation U of power, and that is a glue and quark give you the negative sign, it's a different sign. But and the Q square is more or less flat, but the error bar is large, so I cannot tell that they're 0 exactly that Q square larger. Finite Q square with a 0 in that. That's a good question.
So just to clarify what I was going to say, so in that Dan and mine papers, the last one, so we didn't quote the value for the radius, but I can give you that value if you want. And I'll be very interested to see, because I think my guess is that it's actually going to be very different, because you're getting a very large number. And I think the reason might be that it might actually be that because the mixing is not entirely accounted for, so the gluon F squared part will also depend on the C bar G.
Yeah.
So that might have a very different magnitude for the pion than for the nucleon. So that might be something that is possible to extract.
Yeah, we can look at the
from your
numbers
data.
and see where it comes from, and figure out what the problem is.
But C-bar cancel, right?
Well, it does cancel for the total trace anomaly, but if the mixing is not exactly accounted for and you're just calculating FG, it should mix and have some contribution from the C bar G.
Yeah,
as
there's a
well.
1/8, actually this is 1/8 divergence. Well, you probably discuss, you wanna discuss realization, otherwise it won't be finished. There's a 1/8 divergence, which we'll try to deal with that.
Yes.
So before you go there, if I just compute and Andreas compute F score, so there should be no problem.
It's just the same behavior, it's a constant. Behavior is exactly the same, it's just got no constant.
Just forget about question.
Yeah. So the renormalization we did here on the lattice, because we know there are some operators. So the expression here is mainly from the perturbative expression on the beta over 2G and gamma, and they're derived from the dimensional regularization. But we know there on the lattice there should be some F square operator and psi bar, psi operator, also including some lower dimensional operator, which cannot be excluded, like a 1/A psi bar psi. But what we are doing here is to do the normalization based on the mass sum rule. So one thing here, this whole thing, the matrix element of this whole thing should give the total mass of the hadron. So we know that the beta over 2G and gamma, or the coefficient of these two operators are independent of the hadron state. So we try to solve the mass sum rule equation to get the coefficient of these two operators. But we know there is some lower dimensional operator, but we still calculate these coefficients, which is scheme dependent, using the mass sum rule, using tool of the mass sum here, like the pion rule mass sum, so that we can solve for the coefficients for these two operators. And to check that our calculation, which do not include this lower dimensional operator in this equation, is we look at the ratio where we multiply these factors, which in principle should equal to the hadron mass if there is no significant contribution from the mixed lower dimensional operator, then this ratio should be approximately 1. So that's what we have observed for various valence quark mass on the lattice. So that's why we can think that all these coefficients calculated for this for these operators are relatively reliable to be used.
Well, yeah, I have several confusions.
Many questions, yeah.
These probably I have at least 3. I don't know.
Go for it.
Number 1, that beta and G and gamma are independent of quark mass is something that's usually only true in a particular scheme where you actually calculate as a function of quark mass and do some normalization, actually flow to the chiral limit.
Yeah.
But unless you do that multiple quark mass extrapolation, they actually do depend on the quark mass.
Yeah, but if we see here,
And
yes.
then also in this calculation, you just set HM to 0, right? You haven't calculated.
In this paper, they have already calculated.
Okay. And then in this paper, I guess the last one, maybe this is similar to what I was like, the vector, if the pion mass is light enough, that's in a stable state. So is that actually done with the full pi and q bar q, or is that?
No, you know the answer.
Or was it having a quark mass and it's a stable state?
Put it more fundamental level. There's no conserved energy moment tensor operator on the lattice. Because there's no.
No, I'm just saying defining the vector.
I know, I'm trying to go to the somewhat deeper level before I come to that. There's no such operator. And so there are lattice calculations, we're trying to mix in different operators and make it so that the energy moment tensor is conserved. There's an Italian group, and they have mixed with different operators, M side by side, and side by side with one of a emergence. And then there is Josti has a thermodynamic way of doing it. I don't understand. Probably the best way is the gradient flow. Suzuki has a different sets of operators. You do the small.
I think you're adding a 4th systematic to my list of 3.
Sorry?
I said
You're shooting down his
No, I'm
work.
trying to just get
What are you trying to
these parameters. The summary was the end was is that trying to get there's not an MS bar scheme. It's just a lattice scheme. In lattice scheme, a beta of 2G and the gamma M, without complications of assuming there's not much that complications with other operators mixing. One way we tried to do it, but couldn't put that out. The 2 factors. So that's the way that we can be done now. That the beta of 2G are, if they are scale dependent, depending on the lattice spacing at this moment. We don't know about anything about MS bar or gamma M.
Why did you say that they assumed that beta over 2G was independent of quark mass?
I think Andrew
Andrew
didn't assume that. I think Andrew said you need to actually extrapolate.
Show that.
I'm saying in
Wait,
order
you guys
to
did
make,
assume it?
Uh,
That beta
oh,
over
we-
2G was just some.
well, they said they fixed the quark mass and then applied this for everything.
Yeah, we
just got a number.
fixed these coefficients at one certain valence quark mass, but we apply this for other quark mass, and we didn't see a significant deviation from one.
That's good enough. They tried one and then they checked that the other ones worked.
Normally when you have to do some renormalization, you find your normalization constants have relatively strong quark mass dependence.
Yes.
And then you have to pick a scheme. I'm going to define this normalization constant in the chiral limit, and then you have to do careful extrapolation of those quantities to the chiral limit. And then you have a number that is defined in some scheme, and you understand what that number is.
Wait, but they checked that it didn't depend
No.
on the quark mass.
That's
When they take this equation,
really,
doesn't.
Okay, another
Yeah.
still be a naive question. Sorry, your question.
I'm so confused.
No, wait, can